In pulse echo testing, short pulses of ultrasonic sound are transmitted into a specimen under test. These pulses, in turn, travel through the specimen, reflecting from boundaries, interfaces, in their path. In a specimen with no discontinuities, a pulse travels through the specimen, reflects off the back surface, and all of the reflected energy returns to the transducer at the same time. In a specimen containing a discontinuity, part of the original pulse is reflected at the discontinuity and returns to the transducer before the reflection from the back surface. It is these variations in time-distance relationships, plus echo amplitude, that are used in pulse echo testing to tell us something about a specimen. Shown here is a block diagram of a typical pulse echo instrument coupled to a test specimen. The power supply provides electrical power for all the basic functions of the instrument. The timer circuit controls instrument timing functions such as pulse repetition rate, sweep delay. The sweep circuit controls the CRT sweep functions. And the pulsar circuit, triggered by the timer, generates the high voltage electrical pulses necessary to vibrate the transducer. These pulses being applied simultaneously to the transducer and receiver amplifier. The transducer, in turn, converts the electrical pulses to mechanical vibrations and applies these vibrations to the specimen under test. Specimen reflections, or echoes, are converted back to electrical energy by the transducer, amplified by the receiver amplifier, and applied to the vertical deflection plates of the CRT. The resulting display is called an A-scan presentation. The height of each pip indicates reflected energy amplitude. Their position on the baseline is a measure of time. The initial pulse, or main bang, is the first sharp rise or pip appearing at the left side of the screen. It represents the start of the time base. The precise instant the pulsar applies an electrical pulse to the transducer. In contact testing, it also indicates the front surface of the specimen. An echo from a discontinuity, interface, or boundary always appears to the right of the initial pulse. The more time it takes for an echo to reach the transducer, the farther it appears to the right. At the precise instant the main bang occurs, a pulse of ultrasonic energy is transmitted into the test specimen, providing a front surface indication. As this pulse travels through the specimen, part of it strikes the discontinuity and is reflected. The remainder travels on toward the back surface, where it also is reflected. Since the discontinuity echo has the shorter distance to travel, it arrives back at the transducer first. The height of the resultant pip represents echo amplitude. Its position on the baseline represents the time it took for the trip to the discontinuity and back. The back surface reflection, having the farther distance to travel, arrives back at the transducer later. Its position on the baseline indicates the time required to travel to the back surface and return. Sensitivity or gain controls are provided on the front of the test instrument to adjust pip height. One control generally provides the coarse setting, another the fine setting. The sensitivity or gain can be reduced to the point where only the horizontal trace appears on the CRT, or it can be increased till the screen is saturated, the pips extending beyond the vertical limit of the screen. Normally, sensitivity or gain is set to provide a reflection or echo so many inches high from a known size reflector in a reference standard. More about this in Part 6. Two controls regulate how much of a test specimen is displayed on the CRT screen. One is the sweep delay, the other is sweep range. Adjusting the sweep delay will shift the entire display left or right on the CRT baseline, while the spacing between the indications remain constant. The action is similar to that of moving a ruler back and forth behind a window frame. The markings remain the same distance apart, but we can select the portion of the ruler seen in the window. In contact testing, the sweep delay is generally set to align the initial pulse with a grid line on the left side of the screen. This establishes the starting point for the display. The sweep range control is used to expand or compress the display. What happens is similar to that of stretching a graduated rubber strip behind a window frame. The more the rubber is stretched, the fewer the markings that appear in the window, while decreasing the tension allows more markings to appear. Also notice the starting point does not change, the strip being secured to the left side of the frame. Expansion can occur only from left to right. Contraction is always toward the left. The sweep delay control determines the starting point of an A-scan presentation by shifting the entire display left or right along the CRT baseline. The sweep range control expands or compresses the display without changing the starting point. Expansion and contraction is always away from or toward the left side. Two more controls you should be aware of are pulse length and frequency. The pulse length control, also sometimes called a damping control, is used to adjust the duration or magnitude of the excitation pulse applied to the transducer. A shorter or lower magnitude pulse provides better resolution. A longer or greater magnitude pulse is used to penetrate thicker specimens. The frequency or tuning control is used to match the excitation pulse of the test instrument to the frequency of the transducer. In addition to discontinuity detection, pulse echo is used to measure material thicknesses. As you'll recall, the distance between the initial pulse and the back surface reflection is proportional to the elapsed time it takes for a pulse to travel through a material and return to the transducer. Since velocity is a known constant, the elapsed time, in this example 30 microseconds, represents the thickness of the material. By comparing elapsed time with that obtained from a like material of a known thickness, material thickness can be measured. You should also know that a specimen with parallel front and back surfaces will yield several back surface reflection multiples, depending on the instrument sweep or range setting. These multiple echoes are caused by the sound beam bouncing back and forth in the material, their amplitudes decreasing with increasing multiples. This display shows 5 thicknesses, each pip being exactly the same distance apart. By using several thickness indications instead of one, accuracy is greatly improved. It's possible in ultrasonic testing for the initial pulse to partially block or obscure an echo from a discontinuity located near the test surface. Since the transducer may be still transmitting, it can't receive any reflections. This, you'll recall, is the dead zone, that part of the sound beam in which discontinuities may be masked by the transmitted ultrasonic pulse. The dead zone can be minimized by using a shorter or lower magnitude excitation pulse, using separate transducers to transmit and receive the vibrations, or sometimes the transducer can be moved to the opposite surface of the test specimen. Another way to minimize the dead zone, improve near-surface resolution, is to use the immersion method. In immersion testing, however, there is another factor to consider: water path. It separates the initial pulse or main bang from the front surface reflection, the distance between the two pips representing water travel time. We generally set the water path to be longer in time than that required for a pulse to travel through a specimen and return. This is so the second front surface reflection, also known as a water multiple, won't appear in the same time span as the specimen response indications. It eliminates any possible confusion with relevant indications. Water multiples are easily identified by moving the transducer slightly toward and away from the test specimen while observing the CRT. The first front and the first back surface reflection will move back and forth along the baseline as the water distance varies, but their distance relationship to each other will remain constant. Any pips moving across the screen at twice their rate are water multiples. Proper water path is obtained when no water multiples appear between the first front and first back surface reflection. Once the water path is established, the initial pulse is generally moved off-screen with the sweep delay control. The sweep range control is adjusted to fill the screen. Besides A-scan, two other display presentations are frequently used in pulse echo testing. These are the B-scan and C-scan. The B-scan provides a cross-sectional view of the specimen under test. It shows both the front and back surface reflections, material thicknesses, and the relative location and size of any discontinuities. The display is particularly suited to corrosion testing, or where the distribution and shape of large discontinuities in a given cross-section are of interest. You'll notice a discontinuity masks the back surface reflection directly behind the discontinuity. Where a discontinuity is very small, this is sometimes the only indication that one exists. The image is generally displayed on a CRT screen, the CRT having a fairly long persistence time to retain the image. The time base is positioned between the vertical deflection plates rather than the horizontal plates as in A-scan. The transducer also must be scanned over the specimen, its position being synchronized with the CRT horizontal sweep to control beam intensity. The C-scan presents a plan view indication similar to that of an X-ray picture. It projects the internal details of a specimen into a plane, as seen from the front surface. A separate recorder is generally used, the one shown here being mounted directly on the carriage assembly or bridge. The gating and flaw monitor circuits of an A-scan instrument providing the inputs. The A-scan gating and flaw monitor circuits determine what part of the time base is recorded on C-scan. Also, what amplitude signal will produce a change. Gate position, width, and trigger level, all being adjustable. The carriage is motorized to automatically move the transducer back and forth across the specimen, the scanning speed and indexing being precisely controlled to ensure proper coverage. The more common C-scan recorders use a chemically treated paper that is passed between a printing bar and a helix drum electrically connected to the A-scan instrument. As the drum turns, a sliding contact point between the bar and helix moves across the paper, each revolution producing one line of scan, each line representing one pass of the transducer. As the specimen is scanned, any pips appearing in the gate and exceeding the pre-selected trigger level will cause a change in current flow between the printing bar and the helix drum. It is this change in current flow at the contact point between bar and helix that determines C-scan printout. A less frequently used method or system of ultrasonic testing is through transmission, a method employing two transducers, one solely as the transmitter, the other as the receiver. As in pulse echo testing, the sound beam is generally pulsed, although continuous sound may be used depending on the test instrument. Unlike pulse echo, through transmission involves only the one-way propagation of sound. Echoes returning to the transmitting transducer are ignored. Beam intensity is measured by the amount of energy picked up at the receiving transducer. The soundness or quality of a test specimen is measured in terms of energy lost. In a sound material, the transmitted and received pulses will produce pips of about the same relative amplitude. A discontinuity is indicated by a reduction in the magnitude of sound energy reaching the receiving transducer. The larger the discontinuity, the smaller the received pulse. The display shows only total elapsed time. There is no indication of water travel distance or the depth of a discontinuity. This limits through transmission to special applications where thickness measurement and the depth of a discontinuity are not important. The primary advantage of through transmission is its ability to test thicker materials. A major problem, however, is the alignment of the receiving transducer with the transmitting transducer. Another word of caution when using through transmission with continuous sound. That's the possibility of a resonant condition being set up in the test specimen. Resonance can increase or decrease the magnitude of a discontinuity indication. The remedy, if standing wave interference is suspected, is to select a higher or lower frequency, then observing if a change occurs. Another method is to vary the frequency over a sufficiently wide range that will prevent resonance. In conclusion, pulse echo is the more versatile ultrasonic testing method. It is also the most popular. It can be used for thickness measurement. It requires access to only one surface, and it indicates the depth of discontinuities as well as their relative size. None of these being possible with through transmission. Most ultrasonic test instruments have similar controls for adjusting a CRT display. These include sensitivity or gain controls, sweep range, and sweep delay. The gain or sensitivity can be reduced to the point where only a horizontal line appears, or the pips can be magnified to extend beyond the limits of the screen. The display can be shifted left, right, expanded, or compressed. There is considerable latitude as to what appears and what does not appear. Just how, then, is the presentation made meaningful? How do we establish material thickness, discontinuity size, verify instrument operation? We use some form of calibration block, reference standard. Specifically, calibration blocks are used to check the sensitivity and performance of test instruments and transducers. Reference standards are used to set up or standardize the equipment, establish inspection sensitivity levels, and to evaluate discontinuities. Here is a cross-section of a typical reference standard block. In addition to the parallel ends, notice the artificial discontinuity. It's usually a precisely drilled flat bottom hole. Why a flat bottom hole? It provides an ideal reflector of ultrasonic energy. The maximum amount of energy is reflected back to the source. Sound striking an irregular or cone-shaped surface reflects in many directions. The energy returned to the source is not representative of hole diameter or the size of the artificial discontinuity. Parallelism is very important. And for the standard to be repeatable, the hole diameter A, the metal distance B, and the hole depth C must be precisely controlled. The hole diameter is usually identified in 64ths of an inch, 1/64th, 2/64ths, 3/64ths, and so on. Metal distance may range anywhere from 1/16th inch to 6 inches and more, depending on the particular block. The depth of the drilled hole is usually 3/4 of an inch. The hole is generally sealed. Another important consideration is material. It should be the same as that of the test specimen. The same alloy content, heat treat, the same amount of hot or cold working, the same surface condition. If not, errors will result. For example, using test blocks made from extruded bar stock will lead to large errors in the testing of cast parts. If test blocks of identical material aren't available, they must at least be similar to the test specimen in sound attenuation, velocity, acoustic impedance. Sometimes, instead of using standard reference blocks, a representative sample part is selected and made into a test standard. Known size artificial discontinuities are added, usually in the form of precisely drilled flat-bottom holes. Notches also are commonly used. Tubing and pipe reference standards are often made from representative stock in which precisely machined notches have been added, usually in both the inside and outside diameters, their size being equal to that of a rejectable defect. Many test blocks come in sets designed with a specific purpose in mind. Some provide area amplitude standards and are used to establish sensitivity or reference levels for different size discontinuities found at the same depth. A typical set is the Alcoa Series A ultrasonic references. 8 blocks comprise the set, each measuring 3 3/4 inches long by 1 15/16 inches square. A 3/4 inch deep flat bottom hole is drilled in one end. Each has the same metal distance, 3 inches. Hole diameters, dimension A, range from 1/64 inch in diameter in the number 1 block to 8/64 inch in diameter in the number 8 block. The block numbers identify the diameter of the flat bottom hole. The number 3 block has a 3/64 inch diameter hole. The number 2 block has a 2/64 inch diameter hole. Other block sets provide distance amplitude comparison references for discontinuities of the same size, but at different depths. Typical examples are the Alcoa Series B and the HIT distance amplitude blocks, each set consisting of 19 cylindrical blocks, 2 inches in diameter, each containing a 3/4 inch deep flat bottom hole in one end. Hole diameter, dimension A, depends on the block set, each block in a set having the same diameter hole, the diameters being 3/64, 5/64, and 8/64 inch. Metal distances, dimension B, are 1/16 inch, 1/8 inch through 1 inch in 1/8 inch increments, and 1 1/4 inches through 5 3/4 inches in 1/2 inch increments. A primary application of distance amplitude blocks is in the setting up or standardizing of a test instrument. 2 blocks are generally selected. One with a metal distance as close as possible to the thickness of the material being tested. The other with a metal distance equal to about 10% of the thickness or less, depending on the near surface resolution desired. Flat bottom hole diameter depends on the size discontinuity we want to find. For example, we're interested in discontinuity indications exceeding the response from a 5/64 inch diameter flat bottom hole. We select reference blocks containing a 5/64 hole. Using the block with the greater metal distance, instrument gain is set to provide a given height response from the flat bottom hole. Sweep length is adjusted to represent material thickness. Without changing gain setting, response is checked against the shorter block. It should be the same height. If not, gain is increased till the same amplitude response is obtained. This establishes a range in which discontinuities of a given size or larger are detected, regardless of their depth. In calibrating, standardizing, and immersion setup, distance amplitude blocks are frequently used to establish the initial transducer angle, water travel. Water travel, or water path, you'll recall, is the space between the transducer and front surface of a test specimen, test block. Transducer angle is adjusted via the manipulator to obtain a maximum amplitude front surface indication. A maximum number of back surface pips serves the same purpose, provided surfaces are parallel. The transducer is then moved up and down while observing the CRT for water multiples. proper travel is obtained when the second front surface reflection appears later in time than the first back surface reflection. Distance amplitude blocks also serve as references in evaluating the size of discontinuities at different depths in a test specimen. But keep in mind, the artificial discontinuity provides the ideal reflector. It reflects the maximum amount of energy that a given size discontinuity can reflect. The true discontinuity more than likely will not be perfectly flat or parallel to the test surface. It will reflect something less than the maximum amount of energy back to the source. This means that for a given height CRT indication and metal distance, the true discontinuity invariably is larger than the artificial discontinuity. For example, in scanning a test specimen, a discontinuity indication appears on the CRT. Pip height measures 1.5 inches. Its position on the time baseline indicates the depth to be 3 inches. In comparing the indication with that of a reference standard, it's found a 5/64 inch diameter flat bottom hole at 3 inches metal distance projects the same amplitude discontinuity indication, 1.5 inches. The discontinuity in the test specimen exceeds 5/64 inch in diameter, the diameter of the flat bottom hole in the reference standard. Ultrasonic test specifications often require us to plot distance amplitude curves for each test instrument, transducer combination, for use later in checking calibrations. These curves must be traceable to the test instrument and transducer used, and include such information as instrument control settings, water travel distance, and so on. In plotting a typical response curve, instrument gain first must be standardized. As an example, let's start with a reference block containing a 5/64 inch diameter flat bottom hole, 3 inches metal distance. The transducer is coupled to the block and moved back and forth till a maximum response is obtained from the flat bottom hole. Gain is then adjusted to provide a pip height 50 to 75% of the maximum amplitude indication that can be displayed. If the immersion method is used to couple the transducer, orientation and water travel must be set. The transducer is positioned above the block, slightly off-center, and manipulated until a maximum height front surface indication is obtained, or a maximum number of back surface reflections. Water travel is set where no water multiples appear to the left of the first back reflection, and the distance recorded. The transducer is then moved back and forth till a maximum response is obtained from the flat bottom hole. Gain is set to provide a pip height 50 to 75% of saturation. The point is marked on the graph. Readings are then recorded for each of the remaining blocks in the set, using the same gain setting, maintaining the same water travel, and so on. Once the response curve is plotted, equipment performance can be verified simply by taking 2 or 3 readings and comparing them with the curve. Another block set you should be aware of is the ASTM, or American Society for Testing and Materials Basic Set. This set, comprised of 10 2-inch diameter cylindrical blocks, provides both area amplitude and distance amplitude references. Like the blocks already described, each has a 3/4 inch deep flat bottom hole drilled in one end. 2 have metal distances of 6 inches, 3 with 3 inches, and 1 each with 1.5, 3/4, 1/2, 1/4, and 1/8 inch. Dimension A identifies the flat bottom hole diameter. Dimension B indicates corresponding metal distance. You'll notice 7 of the ASTM blocks contain 5/64 inch diameter holes, varying in metal distance from 1/8 inch to 6 inches. These, plus the 8/64 block with 6 inches metal distance, provide distance amplitude references. Area amplitude relationships are obtained using the 3/64, 5/64, and 8/64 blocks with 3 inches metal distance. Specially designed calibration blocks are often used to check the performance of ultrasonic test instruments, transducers, and establish control settings. Among these is the IIW, or International Institute of Welding block. The -2 version measures 12 inches long by 4 inches wide and 1 inch thick. A step at the curved end of the block reduces thickness to 3/4 of an inch. 5 holes of various diameters are drilled in the block, 4 of which pass through the block. The 5th hole is flat-bottomed. Reference marks are engraved in the front and back sides. A focal point reference is positioned opposite a 90-degree notch. In contact angle beam testing, the exact exit point of the transducer sound beam must be known to accurately locate discontinuities. The point of incidence is easily determined using the IIW block. The transducer is coupled to the block at the focal point reference and moved back and forth till a maximum amplitude pip is obtained from the block radius. At the position this occurs, the sound beam axis or exit point will coincide with the focal point reference. To check or verify an angle beam transducer's incident beam angle, the transducer is coupled to either of the narrow parallel sides of the block and moved back and forth till a peak signal is obtained from the 2-inch diameter hole. The angle of refraction is then read from the appropriate scale on the side of the block. To calibrate angle beam travel distance, the transducer is coupled to the narrow side of the block containing the inch scale and moved back and forth to obtain a maximum amplitude indication from the 2-inch diameter hole. The distance is read on the block's scale, and the test instrument's sweep range is set accordingly. Sweep range can also be calibrated by coupling the transducer to the side of the block near the focal point reference. The transducer is moved back and forth till equal amplitude pips are obtained from the step and the curved edge of the block. The distance between the 2 pips represents 2 inches. To check instrument and transducer sensitivity, the transducer is first coupled to the notched side of the block and moved about till a peak signal is obtained from the desired hole. Instrument gain or sensitivity is set to the desired amplitude. The transducer is then moved to the opposite side of the block to provide a greater travel distance, and the amplitude of the hole reflections compared. Or the block can be laid over and a peak signal obtained from the 5/64 inch diameter flat bottom hole. To repeat the sensitivity setting, transducer distance and the number of bounces from the hole bottom are noted. The IIW block can be used for straight beam distance calibration. The various block thicknesses providing the reflection multiples required to calibrate or set the test instrument sweep range. Another application is in checking test instrument, transducer resolving power. Resolution is indicated by the separation of the pips produced by the 3 reflecting surfaces at the 90-degree notch. Another special block is the miniature size angle beam calibration block. It measures 3 inches long by 1 3/4 inches high, 1 inch thick. A 5/64 inch diameter flat bottom hole is drilled in one side. Like the IIW block, the miniature angle beam block has precisely controlled angles and curves for calibrating test instrument range, determining transducer beam exit point, refraction angles. It also can be used for straight beam distance calibration. Here's the ASME, or American Society of Mechanical Engineers, standard reference plate used in inspecting critical welds. It measures 12 inches long, 6 inches wide by 1/2 inch thick, and contains 6 precisely drilled reference standard holes of various diameters, depths. The reference plate can be used to establish both angle beam and straight beam sensitivity levels. Applications include evaluating the size and depth of discontinuities. Some plates have a V-notch for evaluating surface wave transducers. Test results. Frequently, in ultrasonic thickness measuring, Stepped or tapered gauges are used to check calibration, standardize the equipment. The gauges provide known thickness references and can be read directly from the gauge. Sometimes it's possible to standardize the equipment directly on the material under test, using some other type measuring device to verify or establish the proper control settings. No matter what is used as the reference standard in calibrating or standardizing, be it a sample part or some form of test block, the material properties must be like the material being tested. The same grain structure, hot-cold working, heat treat, the same surface condition. Only then can we assume test results will be valid. In Part 4, you learned that two basic methods are used to couple a transducer to a test specimen. One being the contact method. The other, the immersion method. You learned sound can be transmitted perpendicular to the test surface, at an angle. A special adaptation of contact testing is the transducer wheel. The transducer is mounted on a stationary axle inside a liquid-filled tire. Only the tire touching the specimen. The sound beam can be directed perpendicularly to the test surface as the wheel moves back and forth. It can be directed to the side or angled to the side and forward. The direction of propagation depending on the position of the wheel's mounting yoke. A special adaptation of immersion testing is the bubbler, squirter, or water column. The transducer is coupled to the specimen by a flowing column of water, and depending on bubbler design, both straight beam and angle beam testing is possible. A special immersion application being used more and more is one involving acoustical lenses on the front of a transducer. The example on the left illustrates a spherically focused lens. The one on the right is a cylindrically focused lens. The spherically focused lens concentrates beam energy into a cone-shaped, blunt-pointed beam. The cylindrically focused lens concentrates beam energy into a wedge, the full width of the transducer. With either lens, the angle of focus increases sharply as the sound beam enters the specimen. The focal point moves closer to the transducer, improving surface resolution. Beam intensity increases, improving sensitivity. Beyond the focal point, you'll notice beam divergence increases quite rapidly. This reduces the useful range of the transducer, its depth of penetration. Shorter focal lengths are used to examine areas close to the surface. Longer focal lengths provide deeper penetration. A common application of spherically focused transducers is in examining the bond between two materials. A common application of cylindrically focused transducers is in contour correction, in testing pipe, tubing. Without contour correction, much of the energy is reflected away from the transducer. Refraction and the resulting mode conversion lead to spurious indications. With contour correction, the sound energy is directed normal to the test surface. Any loss of energy or unwanted refraction is minimized. Another device used to reduce beam spread, concentrate sound energy, is the collimator. Its application, however, generally concerns only small, high-frequency transducers. A device frequently used in contact testing is the plastic block, or standoff, cemented to the face of the transducer. The standoff acts much like the water path in immersion testing. It separates the main bang, or initial pulse, from the front surface indication. It improves near-surface resolution. For scanning wide areas at a time at higher frequencies than possible with conventional transducers, there is the paintbrush transducer. It contains a mosaic pattern of small crystals, carefully matched to provide a constant beam intensity. A paintbrush transducer is used to find the discontinuities. Then, a smaller, more sensitive transducer is used to define the size, shape, orientation, and exact location. Till now, we've discussed transducers mostly in the singular sense, either as a transmitter, a receiver, or a single transducer used as both a transmitter and receiver. There are also double transducers, two single transducers mounted in the same holder for pitch and catch testing. One transducer is the transmitter, the other the receiver. They may be mounted side by side for straight beam testing, paired or stacked for angle beam testing. A variation of double transducer testing is the delta technique, so named by the triangular positioning of the transducers. A receiving transducer is positioned normal to the test surface. One or more transmitting transducers are positioned at an angle next to the receiving transducer. Sound energy is transmitted into the specimen and travels at an angle under the receiving transducer. When the sound beam strikes a discontinuity, part of the energy is redirected and picked up by the receiving transducer, producing a discontinuity indication. You'll recall that in addition to discontinuity detection, ultrasonic sound is used to measure material thicknesses. Many ultrasonic instruments are designed specifically for thickness gauging, the thickness appearing either as a direct meter indication or a numerical readout on a digital counter. Simplicity of operation is a key feature of these instruments. Calibration is generally accomplished through a simple screwdriver adjustment or knob setting. Other applications of ultrasonic sound include the determination of differences in material structure and physical properties, hardness testing, all of which generally require special instrumentation, reference standards. Their usage in many cases is limited to the laboratory. Now for the interpretation of test results. You learned in Part 6 that discontinuity indications are compared to those obtained from reference standards. And these comparisons are quite accurate in evaluating size, shape, discontinuity, position. But the CRT display isn't always as easily interpreted as may have been suggested. Often, indications are caused by secondary influences, either in the test system or the specimen itself. Non-relevant indications may be generated. In making evaluations, one must consider the geometry of a specimen, as well as its surface condition. And don't overlook the possible effects of impedance, grain flow, attenuation in the material. The experienced operator develops a knowledge as to what type discontinuities are likely to be encountered, where they're most likely to occur. He learns to discriminate between relevant and non-relevant indications. Non-metallic inclusions, foreign material or porosity in a cast ingot, may be rolled, forged, or extruded into wafer-thin discontinuities. The forces used in fabrication tend to orient the flat plane parallel to the surface. Discontinuities larger than the diameter of the transducer usually produce an indication that saturates the screen. A partial or total loss of back reflection is typical, since the discontinuity reflects nearly all the sound energy. The extent of the discontinuity can be evaluated by noting the distance the transducer can be moved and still receive the indication. Should the discontinuity be three-dimensional as opposed to flat, the extent of the third dimension can be determined by turning the part over and scanning from the opposite side, scanning from an end. Or where two or more discontinuities are suspected, lying close together, the part may be tested from several surfaces. A loss of back reflection is most important when it occurs in the absence of significant individual discontinuities. Common causes may be the test surface condition, large grain size, porosity, or the dispersion of very fine precipitate particles. This view illustrates the effects of surface condition on the propagation of ultrasonic sound. Notice the flat, smooth surface provides a uniform coupling, a highly desirable condition for reliable testing. The rough, irregular surface leads to several undesirable effects. Not only is there a loss of discontinuity and back reflection amplitude, the width of the front surface indication increases, with a consequent loss in resolving power. Wave directivity is distorted. Coarse grain materials, such as that found in me castings, cause multiple reflections of irregular amplitude. The terms grass, hash, metal noise describe this display. Fine grain structures, for example, that found in the high alloy steel forgings, produce relatively clean displays with sharp front and back surface reflections, little metal noise. Materials with excessive fine porosity present CRT patterns similar to that of coarse grain structure. A reduction or loss of back surface reflection occurs, and many discontinuity indications of varying amplitude appear on the CRT. Sometimes a poor response can be improved by experimenting with different incident beam angles, or by lowering the test frequency. But in lowering the test frequency, you should also remember there is a corresponding loss in sensitivity and resolution. The reflection of ultrasonic sound at a boundary can be compared to that of visible light. If the beam incidence is perpendicular to the boundary, it is reflected back to its source, similar to light striking a mirror. Wave propagation is direct, and the least amount of energy is lost. But if the surfaces aren't parallel, the sound energy will be reflected away from the transducer. The result is a reduced back surface indication. In some cases, a complete loss of back surface reflection may occur, depending on the angle of reflection. The possibility of reflections from contoured surfaces, fillets, corners, internal boreholes, must not be overlooked. These indications are sometimes confused as discontinuities, their travel distance being equivalent to that of a true discontinuity. It's a good rule to be suspicious of any discontinuity indication that is unusually consistent in amplitude and appearance during scanning. The true discontinuity is more likely to be strong in localized areas, where a non-relevant indication will tend to remain constant as the transducer is moved over the test surface. In testing cylindrical specimens, especially when the transducer face is not curved to fit the test surface, or a focused lens used, one should be aware of possible non-relevant indications from indirect reflections. Notice the indirect reflection B has the longer path to travel. Its indication appears later in time than the direct reflection. The same is true of non-relevant indications produced through beam spread, mode conversion, in long, narrow specimens. Any newly formed waves that may result from the beam striking the sides of the specimen will have longer paths to travel. This means they'll appear to the right of the first back reflection. Using a larger diameter transducer will reduce the problem of beam spread, or a higher test frequency can be used, but at the expense of penetration power. We're mainly interested, however, only in indications that appear between the front and first back reflections. Indications outside this area can be ignored. With angle beam transducers, there's a certain amount of reflection or reverberation in the plastic wedge. These reflections appear next to the initial pulse and are easily recognized by simply lifting the transducer from the test surface. If the indications are wedge reflections, they'll still appear on the CRT. If not, they'll disappear. Sometimes a crystal may become loose or fracture. The result is a prolonged ringing, which adds a tail to the initial pulse. Should this occur, the transducer should be either discarded or repaired. A discontinuity's orientation can cause variations in depth and size indications. The discontinuity that is located normal to the incident wave will reflect the maximum amount of energy back to the transducer, its pip having the greater amplitude. The discontinuity that isn't normal to the incident wave will reflect something less than the maximum amount of energy back to the transducer. The net result is a reduction in discontinuity amplitude. Position A shows a transducer transmitting ultrasonic energy into a cylinder containing a narrow, crack-like discontinuity. The incident wave is normal to the surface of the discontinuity. We have a sharp discontinuity indication and a fairly low amplitude back surface reflection. As the transducer is moved toward position B, the amplitude of the discontinuity indication will decrease, and the amplitude of the back reflection may tend to increase slightly as a larger part of the incident wave gets past the discontinuity. You'll notice the discontinuity not only decreases in amplitude, it tends to spread out over a longer time period. At position C, the discontinuity indication will be minimal. In fact, if the discontinuity is very narrow, no indication may appear at all from the discontinuity, and the back reflection may have an amplitude like that from a sound specimen. As you'll recall, two basic techniques are used in locating and evaluating angular discontinuities. In contact testing, an angle beam transducer is used to change the direction of wave propagation. In immersion testing, the transducer is simply angulated. Through refraction, mode conversion, the direction of wave propagation is altered to locate discontinuities which might otherwise go undetected. The surface condition of a discontinuity influences discontinuity indications in much the same manner as an interface or material boundary affects ultrasonic energy. A discontinuity with a rough surface tends to scatter its reflection. The result is a lower amplitude discontinuity indication than one from a similar size, smooth surface discontinuity, the smooth surface reflecting a more refined beam. You'll recall from the discussions on test blocks that the effective distance on discontinuity amplitude is quite appreciable. When amplitude is plotted against the distance from a specimen's front surface, pip height first increases with increasing distance to a maximum value, then decays almost exponentially. A discontinuity, for example, 6 inches from the test surface, might produce an indication twice as high as a discontinuity of the same size, 2 or 13 inches from the front surface. The extent of this relationship varies considerably from one material to another. In summation, these factors affect the size of discontinuity indications. Orientation of the discontinuity in relation to specimen front surface. Surface condition of the discontinuity, whether or not it provides a rough or smooth reflector. The depth of the discontinuity. One also must consider incident beam angles, indication amplitude, travel distances, loss of back reflection. These factors tend to limit the use of ultrasonic testing. Foremost is an unfavorable geometry. Complex shapes, contour, the size of a test specimen. An undesirable internal structure, such as large grain size, excessive porosity, inclusion content. Excessively rough surfaces. Should any or a combination of these limitations make ultrasonic testing the undesirable choice for a given test, some other form of non-destructive testing should be selected. Ultrasonic testing demands that you have a knowledge of a test specimen's material, construction, a clear definition of tests to be performed. There must be adequate reference standards for making comparisons, good test procedures, realistic acceptance standards. And last but not least, the equipment must be calibrated, standardized.